Hey, well, it's a great pleasure to welcome Liz Stanhope from Lewis and Clark College, who will speak on using Hodge spectra to detect orbifold singularities.
Uh, Thank you so much. Yeah, so I'm Liz Stanhope. Nice to meet you all virtually today. Yeah, so I want to thank first Fernando, Carolyn, Ramiro, and Emilio for organizing this really cool cloud seminar. I appreciate the opportunity to speak very much. Okay, so yeah, I'll be talking about using Hodge spectra to detect orbifold singularities. Let me see if I can use my computer. I can. So overall, so I'll start with an overview of the results I'd like to highlight today. Then I'll jump into a little bit about orbifolds and what we can tell about orbifolds using their Laplace spectra. Um, After that, we'll shift over to using the Hodge Laplacian, particularly on 0 and 1 forms for starters, and then looking at the Hodge Laplacian just for p spectra alone, and again trying to say things about orbifold structure using these spectra. So that's the overview. Right there. So I also want to acknowledge wonderful collaborators, many of whom are virtually here today. So this work is coming from two papers. The first paper came from this Women in Geometry Workshop 2 group we met in Oaxaca, Mexico, which was amazing. That was Magna Khalil, Katie Gittins, Carolyn Gordon, Mary Sandoval, and Ingrid Membrio Solis. And then the second paper, we were lucky for us to have Juan Pablo Rossetti join us in that second paper work. So yes, these are all the collaborators on this work. Hopefully I'll do justice to our work. I'll try my best. Okay, so the results I'd like to talk about. So this paper 24 is from the first group that worked, and the second one is going to appear in the Michigan Math Journal. So positive results. So if you use the 0 spectrum and the 1 spectrum together, we've shown that you can distinguish Riemannian orbifolds with singular sets of codimension less or equal to 3 from closed Riemannian manifolds. That's really the big question in the spectral geometry of orbifolds, in my opinion, is can you hear the singular set? Can you detect it? And that question is open with just the Laplace spectrum. It's not known whether or not a manifold and a singular orbifold can be Laplace isospectral. But we got some results here throwing together a couple of spectra. Another positive result is that in some cases, the p spectrum, so that's the Hodge Laplacian acting on p forms, so the p spectrum of a Riemannian manifold in some cases will determine the volume of the singular set of that orbifold and actually distinguish the orbifold from manifolds because it has a singular set to have a volume. In this talk, I'm assuming all orbifolds and manifolds are compact, connected, and without boundary, with empty boundary. Let's see. So some negative results. So the p spectrum isn't as strong maybe as we would hope. In every even dimension, we've shown that you could find a manifold and a singular orbifold that are p isospectral for all p's, for all odd p. So in that case, you can't detect the singular set using that p spectrum. And we also have examples of pairs of p isospectral manifolds where one is orientable and the other is not. And orbifold pairs too. Although I think personally the manifold example is more interesting. That is open in the setting of manifolds for the Laplace spectrum. So it's not known amongst closed manifolds whether or not an orientable manifold can be Laplace spectral to a non-orientable manifold. It is known in the setting of manifolds with boundary though. Okay, so those are where I'm heading to. So let me check in on orbifolds and what those are and discuss what we can tell using their Laplace spectrum. So what is an orbifold? So an orbifold is a mildly singular generalization of a manifold. I'm going to try to use a zoom tool. Let's go. Where's this pointer? Here we go. Yeah, so it's a mildly singular generalization of a manifold. They were defined by Satake in 1950 and show up in a variety of branches of mathematics, particularly where there are quotients involved. Just like a manifold, you build an orbifold, starting with, a second countable Hausdorff space and patching together an atlas of charts. And in this case, we'll be using orbifold charts. Here's a picture of an orbifold I'll use as an example in this talk. I call it the waffle cone. So there's the waffle cone. It'll come up a bunch. So what is an orbifold chart? So a d-dimensional orbifold coordinate chart is a triple associated with a connected open set in the orbifold. So this is my set in the orbifold U. The triple is U tilde, a connected open subset of our D. We have gamma U, which is a finite group acting on U tilde by diffeomorphisms. And then we have a mapping pi, which gives us a homeomorphism between the quotient of u tilde under this finite action gamma u onto the neighborhood of the orbifold. So informally speaking, an orbifold looks like a local quotient of a patch in RD, an open set in RD under a finite group action. So let's take a look back at that waffle cone as an example. I'm going to concentrate on the orbifold here. This is a two-dimensional orbifold. It's a surface. In this case, points just along the edge of the orbifold, along the side of it, are just normal manifold points. They look just like points in a manifold. Down at the bottom here, you have this sharp point. It's a cone point. This can be modeled on the quotient of a disk under rotations of order 3, so rotations by 2 pi over 3, so a finite group of order 3. If you take the quotient of that disk under that finite group, you get this wonderful cone structure. Up here is a corner reflector. So that again is the quotient of a disk now under the action of a dihedral group of order 6. The reflections give you this corner shape to it. And then all along the edge here, which looks like boundary, this looks like an object with boundary. From the orbifold perspective, this isn't boundary, because each point here is modeled on the quotient of a disk under a reflection across a diameter of that disk right there. So one really pretty thing I like to, especially geometry with symmetries, that I like to talk about is that every wallpaper group has a corresponding orbifold. So this waffle cone can be obtained as the quotient of the plane under the wallpaper group that preserves the symmetry of these goofy shapes. I should say this art is from a text by Conway, Bergiel, and Goodman Strauss. They have beautiful images of all the wallpaper groups. So if you look at, for example, these blue dots, that's the orbit of a point under that wallpaper group. When you take the quotient of the plane under that big wallpaper group, the blue dots will all map to the cone point in the orbifold. You can see that there's this threefold rotational symmetry around the blue dots. Similarly, along the edges here, you have a wonderful reflection, giving us that reflector edge structure along the reflector edge of the orbifold. And then here where you see the reflector edges coming together with rotations, that rotational symmetry as well as reflection, we get that corner reflector up here. So a really fun way to cook up orbifolds in dimension 2 is to look at wallpaper groups. So what makes an orbifold interesting is that it has a stratification by singular points. So how do we do that? So take a point in your orbifold, just point X. You have that local quotient structure, so take a lift of that point in u tilde, that local neighborhood around it that we're taking the quotient of. Since gamma u is acting on u tilde, there's going to be an isotropy subgroup of gamma u associated to x tilde. So we'll take that isotropy subgroup. All of the elements of that subgroup are diffeomorphisms, so we can take their differentials. And in doing so, we can view we get an orthogonal representation of that isotropy subgroup. So we can view the isotropy subgroup as a subgroup of the orthogonal group in dimension D. So the isotropy type of the point X in the orbifold is then the conjugacy class of this finite subgroup in the full orthogonal group right there. So that's our isotropy type. And this leads us to a nice structure to the singular points in the orbifold. So a point in an orbifold is singular if it has a non-trivial isotropy type. So 2 points in an orbifold are defined to be isotropy equivalent if they have the same isotropy type. And then when you look at the equivalence classes and you take connected components of these equivalence classes, you get the singular strata that characterize the orbifold structure. So just going back up here to the waffle cone, we have a lovely stratification. There's the big manifold strata of points that have trivial isotropy. And then we have 3 distinct orbifold singular strata. One is a 0-dimensional stratum corresponding to this cone point. We have another 0-dimensional stratum, has different isotropy. It has that full dihedral isotropy. And then we have a 1-dimensional singular stratum, which is this entire edge of mirror points right there. So we have strata for this 2 orbifold. We have strata of all possible dimensions, 0 and 1 dimension. Okay, so we've got our singular strata. What about doing geometry on orbifolds? So if you take Riemannian metrics on these local covers U tilde that are invariant, under Riemannian metric on those U tilde, then you can patch them together to get a full Riemannian metric on the orbifold. So geometry is in play. And similarly, you can carry over the tools of spectral geometry to orbifolds. The spectral theorem extends to the orbifold setting. So here, once we have our Laplace operator, we can look at its spectrum. And just like in the manifold case, the Laplace spectrum of the orbifold is going to be a sequence of non-negative real numbers heading off to positive infinity, where each eigenvalue has at most finite multiplicity. So we can talk about the spectral geometry of orbifolds. Some early results in the question of can you hear the shape of an orbifold? One was in 2001 by Carla Farsi. She showed that Weyl's asymptotic formula extends from the manifold setting to the orbifold setting. And that formula talks about how the eigenvalues are growing as they diverge to positive infinity. So the growth of the eigenvalues has an asymptotic expression, and in that expression, you pick up the dimension and the volume of the orbifold, just like in the manifold setting. So in short, the Laplace spectrum of an orbifold tells you its dimension and its volume. In 2006, Naveed Shams, myself, and David Webb cooked up some Laplace isospectral orbifolds with topologically distinct singular sets. This is really early results, simply saying you can't hear the topology of the singular set. The singular stratification in these orbifolds had different numbers of connected components. And then shortly after that, Juan Pablo Rossetti, Dorothy Schutt, and Martin Wieland showed examples of isospectral orbifolds that have maximal isotropy of different orders. So you can think of like a really narrow cone point as really high isotropy and a really wide cone point as low isotropy. In their examples, that maximal isotropy that appears in the orbifold are different. Okay, so I'll now shift over to the focus of this talk, which is the question, can you hear the singular set of an orbifold? Does the Laplace spectrum detect the singular set? So two results in this direction. And I will say that's open, so it's not known if the Laplace spectrum of an orbifold will detect the singular set of the orbifold, but we have progress. So Rossetti and Gordon in 2008 showed that if you have a singular orbifold and a manifold that share a common homogeneous Riemannian cover, they cannot be isospectral. So a fun example to think about again is the waffle cone and the torus, right? The torus is a nice manifold. The waffle cone is a wonderful singular orbifold. They can't be isospectral because they're both quotients of the plane. And then in 2010, Craig Sutton extended this a bit by showing that you don't need this common cover, common Riemannian cover. It's sufficient to have isospectral finite Riemannian covers for your orbifold and your manifold to get this abstraction to isospectrality. And then I want to talk about this really nice results from Emily Dryden and then Carolyn Gordon, Sarah Greenwald, and David Webb. And this sets us up for the later results I'll talk about when we pull in the Hodge spectrum. So they showed in 2008 that a singular orbifold that possesses a primary opposite parity stratum cannot be isospectral to a manifold. So what does this mean? So the waffle cone is a two-dimensional orbifold, but it has a one-dimensional singular stratum, all of the mirror points right there. So they're saying that a one-dimensional stratum has opposite parity to a two-dimensional orbifold. Thus, that will never be isospectral to a manifold because of this mismatch of the parity of the stratum to the dimension of the orbifold. And then in the same paper, they showed that if you looked at all singular two orbifolds, of which the waffle cone is one, excluding those with hyperbolic structure and lots of cone points, then no orbifold in that collection could be isospectral to a smooth surface. So this is using the Laplace spectrum. So let's dig in a little bit. Oh, right, I didn't define primary. Let me check in on that because it shows up and it should be defined. So what is a primary singular stratum? It's really a technical condition here. So we have a singular stratum and it is associated to its isotropy group. So the stratum is defined by the group that fixes the points in the stratum. We're going to look at a subset, iso star, of that isotropy group. So it's not a subgroup, but just a subset. We'll go through all of the elements of the isotropy group of N and pick out only those for which the dimension of the stratum matches the dimension of the fixed point set of the particular mapping gamma right there. And it's primary if isostar is non-empty. A good example to think about is one of these corner reflectors here. So corresponding to this point up here in, the plane where we have reflections and rotations, notice that the rotations, so if gamma is a rotation, the rotations only fix a central point, and that point has the same dimension as our stratum, our zero stratum here, dimension 0. So those will be an isostar as opposed to the reflections. So if you choose a reflection out of the isotropy group, those fix an entire line of points, which is higher dimension than the stratum itself. So those will not be an isostar. So this certainly is a primary singular stratum, this corner reflector, because of those rotations. A nice example from the paper by Gordon, Greenwald, Dryden, and Webb is this is a non-primary singular stratum. So to see that, we take R3 and we act on it by rotating around each coordinate axis by pi radians. So just a rotation. From this rotation, for example, the positive x-axis is rotated to the negative x-axis. So if you take the quotient of R3 under this action by the Klein-4 group, you end up with something like this, where you have a central node and then the images of the axes coming out of it. This central node here, the blue node here, has full isotropy. The entire Klein-4 group fixes it. So it's a singular stratum of dimension 0 with full isotropy. But when you hop up to the cover, all of those rotations fix the entire axis. There's no element of the isotropy group of this point that fixes only the point. So this really fun node between these edges is not a primary singular stratum. And what happens is we'll be using heat invariants for our arguments in this talk. These stratum are, in a sense, too small to contribute to the heat invariance. Okay, let's see. Oh, and I want to point out too that when you look at the singular stratification of an orbifold, whatever stratum has highest dimension, that will always be primary. So it's a handy fact to have around. So let's dig a little bit into how Dryden, Gordon, Greenwald, and Webb approached their proof. They use the heat invariants associated to an orbifold or a manifold. So to start with, we'll take the heat operator and the associated heat trace to the heat operator. So the associated heat kernel of the heat operator. So there's our heat kernel. Here we have e to the minus t times our eigenvalues, and then the normalized eigenfunctions appearing. In 1970, Berger, Godechon, and Mazet showed that if you take the heat trace, so you're taking the trace of the heat kernel over your manifold, we get this wonderful sum, which depends on the eigenvalues in particular. And as t goes to 0, imagine t being 0, you're adding 1 to itself infinitely many times. So as t goes to 0, this blows up. And the way that it blows up is asymptotic to an expression of the form here. We see these ak appearing as coefficients of t to the k in this sum, and those are the invariants called the heat invariants. And the idea is, I should say, that the heat invariants are things that we can read off from the spectrum, because the sum depends on the eigenvalues. The Laplace spectrum lets us access the heat invariants as well as the dimension of our manifold. The first heat invariant, A0, sorry about scrolling back and forth. When k is equal to 0, we get a T0 here, we get an A0, so that's our first one. The first heat invariant is the volume of the manifold. I guess it's the 0th heat invariant. The one after that, A1, is 1/6 of the integral of the total, 1/6 of the total scalar curvature of our manifold, which is nice because in dimension 2, that lets us detect the Euler characteristic of a manifold using the heat invariants. And then later heat invariants, A2, A3, are integrals of sums involving the curvature and its covariant derivatives. They get pretty complicated pretty fast. So how were the results above shown? The first step of the work was to follow work by Donnelly to show that a d-dimensional orbifold has, again, it has heat trace as before, and its asymptotic expansion looks like this right here. So an interesting feature is here we have a j/2 appearing in the exponent, but it's very similar to the heat trace for a manifold. And then importantly, they showed that this expression broke up into two pieces. We have an I0, and then we have a sum here. this sum is over n strata in the orbifold that are primary. So this is the set of all primary strata in the orbifold, and we're adding up all of those contributions from each stratum. A little more details here. So I0, again, looks very familiar from the manifold setting. So we get the manifold heat invariance. And then in addition to those heat invariants, we get this contribution here where In is now of this form. In this coefficient, we have the dimension of the singular stratum appearing, as well as a new set of invariants BK, which are orbifold heat invariants. So that's the main tool of their work. Again, because these expansions are determined by the spectrum of the orbifold, isospectral orbifolds have to have identical heat expansions. So from this, if you look at it for a minute, you can see how the opposite parity theorem came to be. For example, if you're looking at a two-dimensional orbifold, over here you'll have two-dimensional orbifold, 2 over 2, so this turns into a 1. And these are t to the k. So on this side, the I0 term will always have integer coefficients or integer exponents of t. On this side, though, for example, if you have your stratum of mirror points, that one-dimensional stratum, here you'll get a 1, so you'll have a 1/2 appearing as a minus a half appearing as an exponent of t. It'll turn out, and we'll see this soon, that B0, the zeroth heat invariant here, is always non-zero. So you definitely will get a contribution with a half integer power on this side. So the fact that in the manifold, we'll always have, at least in dimension 2, integral exponents, but here we'll have a half power exponent of t, means that we can detect the existence of that singular stratum. And just to touch on their second result, suppose C again is that set of orbifolds, excluding ones with lots and lots of cone points. They asserted that no orbifold in that collection can be isospectral to a surface. So first of all, they looked at orbifolds with mirror edges, and that's an opposite parity stratum, so those can't be isospectral to the surface. And then they looked at orbifolds with only cone points and dug into these B sub k, these orbifold heat invariants, and with some computation, found this spectral invariant, so twice the Euler characteristic plus a sum here involving the orders of all of the cone points in the surface, and that was enough to distinguish the orbifolds in the collection from the manifolds. Really neat result and really nice way to lay the groundwork for the results I'd like to talk about from my collaborative work. So what about when we take the Hodge Laplacian and look at its spectrum here? What can we say? So just to check in, here's the usual Laplace operator here, minus divergence of the gradient. The Hodge Laplacian is acting on p forms, and here it's expressed as d, which is the exterior derivative of our p forms, and then its adjoint acting as well. So this is our Hodge Laplacian. In 1999, Buchikovic showed that the Hodge Laplacian of an orbifold has a discrete spectrum, much like the familiar spectra we're working with the Laplace operator. I'll decorate now our spectra with little p's up here to tell us what we're operating on. If p is equal to 0, we get functions, and otherwise we're operating on p forms with the Hodge Laplacian. One early result using the Hodge Laplacian on orbifolds was by Gordon and Rossetti in 2003. And they showed that if you're in an even dimension, the middle degree Hodge spectrum, so that's half of the even dimension, that middle degree Hodge spectrum can't distinguish manifolds from singular orbifolds. This is a negative result. You can't hear the singular set in these examples. And for those who are curious, it's not a Sonatas theorem result because they don't get isospectrality for all p. These examples that they create are not isospectral on functions. So what do we do? So we want to hear the singular set. So my first big collaborative group showed if you combine forces, you take your 0 spectrum and your 1 spectrum, then we can hear the singular sets when the singular sets are relatively large, codimension less than or equal to 3. And a nice corollary of that result is if you just look at dimensions less than or equal to 3, Codimension less than or equal to 3 doesn't give a lot of wiggle room. So in that case, for dimensions less than or equal to 3, the 0 spectrum together with the 1 spectrum distinguish singular closed orbifolds from closed manifolds. So wrapping up that case in dimension 2, for example, that was left open, the double whammy of 2 spectra is enough to hear that singular set. So I'd like to say a bit about the proof here. So the first part of the work, which was a significant part of the work, was extending the orbifold asymptotic expansion of the heat trace for the Laplacian on functions by Dryden, Gordon, Greenwald, and Webb to the setting of p-forms. So we showed that we do get an expansion of this form. Again, super familiar, but now we're decorating our invariants with the letter p to indicate that we're working on p-forms with the Hodge Laplacian. We followed methods by Gaffney and Patodi, as well as Donnelly and the previous group. And the hard part was just to follow all the details very carefully in that literature. Once we obtained the heat invariants for the Hodge Laplacian on p-forms, how do we jump into that proof? So if we have a Riemannian orbifold whose singular set has codimension 1 or 3, that implies that this biggest stratum, which is giving us this codimension, has opposite parity, and then the 0 spectrum, as we've seen before, is enough to distinguish the orbifold from the manifold. So the interesting part of the proof is to look at orbifolds whose largest stratum has codimension 2. Note that we can't have a codimension d minus, or we can't have a higher dimensional stratum in these orbifolds, otherwise we'd have codimension 1. So this codimension 2 stratum with dimension d minus 2 has maximal isotropy and thus is primary. So it will be detected by the orbifold heat invariance. It doesn't vanish, which is good. So let's think about how this codimension 2 stratum contributes to the heat invariance in this case. This is just a pile of symbols here. Just wanted to get it into one place, right? So we're curious to see where the stratum is going to contribute to the heat invariance, which combine these manifold heat invariants with these new orbifold heat invariants. So an observation is because we have this exponent here, negative dimension of the stratum over 2, our highest dimensional stratum, so our dimension, codimension 2 stratum, so d minus 2 dimensional stratum, is the only strata, all of those strata are the only ones that contribute to the lowest degree term in the right-hand side. So the right-hand side here, we have t to the k, right? So k equals 0 to infinity. Here we'll have degree k, but that gets combined with this t to the minus dimension of the stratum over 2. So that lowest degree term occurs for the highest dimensional stratum, which is the strata that we're focusing on here. If you stare at it for a while, that lowest degree term on the right-hand side is going to have degree 1 minus d over 2. So if you take t to the 1 minus d over 2 over here, what is the t to the 1 minus d over 2 contribution over here, right? And this is easier to see if you take t to the first, then you have, I've lost my dot. If you take t to the first here, then you have your minus d over 2 here. So it's just going to be an a sub 1 heat invariant contributing from this side. So in summary, the full coefficient of t to the 1 minus d over 2 in heat expansion has this form. This is the thing that the spectrum gives us. So if we know the spectrum of our object, we can pick up this expression right here. Again, here we have a manifold heat invariant. The p is indicating it could be for any the Hodge Laplacian on p forms. And again, I'm not committing to what degree p differential form we're working on, but you see that you get your orbifold heat invariant here. I should indicate down here, we're now focusing on only those singular stratum of codimension 2. That's what this is trying to indicate, because those are the only ones who contribute to this lowest degree term t. Okay, so a really beautiful observation from the manifold setting is if you look at the first heat invariant on functions and the first heat invariant on one forms, you get these integrals of the scalar curvature. For one forms, it's coefficient d minus 6 over 6, and then for functions, it's 1/6 right there. So you have a relationship between these two different heat invariants. And here very much we're using the Laplace spectral heat invariance and the Hodge Laplace heat invariance. That's how that connection happens. So we get this beautiful equation. If we have a manifold, this equation will be true. So the strategy of this proof is to show that this equation is broken in the presence of a singular stratum. So if we have an orbifold with one of these codimension 2 strata, and we compute the relationship between these heat invariants, the presence of this strata contribution is going to break this equation, and then we'll know we have an orbifold. So that's our strategy. So it takes digging into this expression and making sure it doesn't satisfy this lovely relationship right here. So again, we complete the proof here by showing when you multiply this zeroth heat invariant on functions by d minus 6 for a particular stratum of codimension 2, it's going to be strictly less than the corresponding heat invariant on 1 forms. So how do we prove that? So we have to dig into what these invariants actually are. The zeroth heat invariant for the Hodge Laplacian P forms on our orbifold is going to be the volume of whatever your singular stratum is, times the sum again of these isotropy elements that are in iso star of this contribution based on whatever isotropy element we have. Here I break this piece out for the Laplacian on functions and the Hodge Laplacian on 1 forms. The numerators are fine. This is the trace of whatever isotropy element we're working with. The denominators are a little more complicated. What does this mean? So we take our isotropy element and represent it as a bunch of fixed directions. So these are all ones. This is an identity matrix corresponding to the d minus 2-dimensional singular stratum. That's a fixed point set. And then a gamma, which is now going to be a 2 by 2 matrix right here. And because it's not allowed to fix anything more, because then we would have a higher dimensional stratum, a d minus 1 stratum, it turns out that all of the A gammas together for elements of our isotropy group form a subgroup of rotations, a cyclic subgroup of order M in SO2 cross the identity d minus 2 here. So that order M is nice to keep around. So we're saying, again, that the isotropy subgroup of here is characterized by a cyclic subgroup here with fixed directions. So we go to compute these by taking the determinant of the identity minus this little piece right here and putting that in absolute value in the denominator. So if you sit down and work it out, we find that the zeroth heat invariant on functions, in this case, is that rotational order, m squared minus 1 over 12 times the volume of our singular stratum. And then the similar expression on 1 forms has a more complicated coefficient, but not too complicated. And if you compare them, so I subtract one from the other, and we find that we get 3m squared minus 6m plus 3 over 6, which for cyclic groups of order greater than or equal to 2, which is what we care about, because order 1 is trivial. We don't want those. This, in fact, is positive, showing the inequality that we want, that the contribution from 1 forms from our singular stratum is going to be strictly greater than d minus 6 times the contribution from our stratum from the spectrum on functions right there. And that does it right there. So that allows us to detect that singular stratum because we violate the equation that's true if there is no singular stratum. Okay, pause for a second. That was a lot. So it's to me such a fun result. But let me shift for a second. So that's using the 0 spectrum and the 1 spectrum together. So what can we say about the individual P spectra, building off of that work by Gordon and Rossetti from 2003? To do that, we took a closer look at this 0th orbifold heat invariant corresponding to the Hodge Laplacian acting on P forms, right? So now not just functions and 1 forms, let's see what happens if we keep the P in the expression above. It has very much a similar form to what we saw before. Except for the numerator here, where we have the P trace of our isotropy element gamma. And that's going to be the trace of the action of this isotropy element gamma on the p forms on Rn. So that trace appears right there. So just keep in mind, that's what this zeroth heat invariant looks like. We're going to sneak into one case only, which looks simple, but is really wonderful. So we'll take a singular stratum of codimension k and require it to have isotropy of order 2. So a really simple isotropy group, just order 2. Take gamma generator of the isotropy group. Then when you sit down and compute this p trace, you'll find it has this form, excuse me, right here. So we have a sum j from 0 to p of an alternating piece, and then we have k choose j, d minus k choose p minus j. So this beautiful combinatorial expression where things go to 0 when they don't make sense. So if n is bigger than m, we put in 0 there. Okay, so that's the p trace for gamma when we have this special situation of an isotropy group of order 2. It turns out that combinatorists have been working with expressions of this form. So what we just saw as the p trace is the value at k of the binary Krauschock polynomial of degree p. So this k here, kdp of x, this is what I'll use to denote these Krauschock polynomials. And exactly the same form appears where previously we had a k, and now we have a variable x. So with some computation, this lets us express the zeroth heat invariant for the Hodge Laplacian acting on p forms of a singular stratum of codimension k in this form right here when we have isotropy of order 2. Super nice. Especially interesting is that the zeros of this Krauschock polynomial match up exactly with the zeros of this particular heat invariant. This is intriguing. So the vanishing of these particular heat invariants corresponding to our singular stratum n means that singular stratum does not contribute to the corresponding part of the heat invariance. In a way that the heat invariants are missing the presence of this stratum in this place. This suggests, it certainly doesn't prove anything, but it suggests that the zeros of the Krauschock polynomials could lead us to a place where we can't detect can't detect a singular stratum. So maybe we could find a singular orbifold that's p isospectral to a manifold in this situation. And indeed we can. So it takes some construction. But here we go. Just bear with me for a moment. So we're trying to look for manifold orbifold pairs that are p isospectral. To do it, we will look at the following setup. So we want a dimension greater than or equal to 2, and k is any number between 1 and d minus 1. We define this mapping gamma sub k from Rd to Rd. What does it do? It's going to negate the first k components of my d tuple and leave the remaining components fixed. Nothing is going on there. So that's our first tool. We'll use this this mapping, this I view it as an isotropy element. We'll use this mapping in what follows, but we want to adjust it slightly to get a related mapping. So here we have A, so this is going to be another D tuple, so it's in the D-fold product of the half integers. So take A of this form, but make sure that somewhere in these last D minus K entries of A, one of them is equal to 1/2 right there. And we'll take rho K to be equal to gamma sub K, composed with left translation by A. So we'll translate, and then we'll hit the point by gamma sub K right there. And I hope by looking at this, your intuition suggests that rho K is fixed point free in a way, and gamma K is going to lead to some fixed points, and that's true. But first, we need to get ourselves some manifolds and orbifolds to work on. So what we're going to do is I'll just focus on sigma k for starters. So sigma k is going to be a discrete subgroup of the Euclidean motion group. How do we get it? We take all of the translations. Here's that big integer lattice of translations in dimension k. And then we throw in gamma k, and we generate some subgroup of the Euclidean motion group. So that'll give us this big sigma k. If we take the quotient of Rd by this sigma k, we'll get an orbifold. I'm asserting it's an orbifold to consider. Similarly, sigma k prime is going to instead use the rho k to generate an interesting subgroup of the Euclidean motions, again, together with the integer translation lattice. So here we'll get OK and MK as the corresponding quotients. So using some really wonderful techniques developed by Roberto Miatello and Juan Pablo Rossetti, you can show that if the corresponding Krautchuk polynomial, so the dp Krautchuk polynomial, vanishes at k, right here, then this pair OK and MK are p isospectral. I'll jump to this last line here. MK is a manifold for all k, and OK is always going to be a singular orbifold. Just note that. So we get these wonderful p isospectral pairs of manifolds and singular orbifolds. Another fun result is that if k prime is another element of the list from 1 to d minus 1, then we in fact have a family of 4 objects that are mutually p isospectral, using this other k prime to define, just where did that k fit in, right? The number of entries that get negated at the beginning of gamma k, right there. Okay, so this is a proposition. It asserts there's a technique to get isospectral orbifolds and manifolds. There's a big if. Where's my if? Right, if the Krautchuk polynomial vanishes at k, right there. And I will say we're in that nice combinatoric situation from above because we do get order 2 isotropy for the singular points in OK. So we can apply all of those tools that we have using the Krautchuk polynomials. So let's apply this method here. When d is even and p is odd, it is known from the combinatorics literature that kdp at d over 2 is equal to 0. So what we end up with here are manifold and a singular orbifold in any even dimension, because d is even, that are p isospectral for odd p, right there. So we see that it's a large case of even dimensions and odd p isospectrality where we can't pick up the singular set of an orbifold. So in a sense, you could say that the p spectrum is weak in this situation for not picking it up. And then using the same proposition in a different application of Krautchuk polynomials, we make an observation. So it's kind of fun combinatorics. If k is a 0 of the Krautchuk polynomial dp of x, k dp of x, then so is d minus k. You kind of reverse the roles of your x and d minus x, and you get another 0. So suppose d is odd, and we have a Krautchuk polynomial vanishing at k. Then using the proposition above, we end up with this element of 4 p isospectral objects, mk, md minus k, etc. Right here. And what's interesting is if d is odd, for example, and k is also odd, we'll get an even number here on the d minus k, while k is odd. If d is odd and k is even, here we'll get an odd number, but k will be even. In our work, we show that mk and ok are only orientable if k is even. So in this collection, by this choice of d being odd and this d minus k property, we're guaranteed that there will be orientable and non-orientable elements of the family, which again is so interesting that we have, for example, an orientable and non-orientable manifold that are p isospectral. Should we have this vanishing property of the Krautchuk polynomial, in contrast to the 0 spectrum where this is still open. And I will say that this does happen. So there are odd d's for which the Krautchuk polynomial vanishes. When d is an odd square, there are examples. So it's not just an if, but we actually can do it in some cases there. Okay, so in a sense, maybe I'm insulting the p spectrum for calling it weak, but we do actually get nice results from the p spectrum. Let me dip into those. So suppose I have a d-dimensional Riemannian orbifold with singular set of odd codimension k, and then choose p between 0 and d. Then if the corresponding Krautchuk polynomial doesn't vanish, we can show the p spectrum determines the volume of the singular set in the orbifold. And what is that volume? So the singular set is a kind of an odd structure as a whole in the manifold. So you take the top dimension of the strata, whatever that is, and use the Hausdorff measure of that dimension to get its volume. So in any case, using these hypotheses, the p spectrum determines the volume of the singular set, and certainly that will distinguish the orbifold from a manifold if we can here how big that singular set is. In a manifold, it's going to be empty, so volume 0. So I'll sketch this result and how it is done. It's again using the nice combinatorics from above. So we'll take a singular stratum of codimension k. Because n has maximum singular dimension, all non-trivial elements of the isotropy group have the same one eigenspace. Again, if they had different one eigenspaces, we would have a higher dimensional singular set. So this isotropy group of n can be expressed as a product of some group gamma cross the identity corresponding to the fixed directions that lead to this singular stratum. And then here gamma is a finite subgroup of the orthogonal group in dimension k. That's what's left over after we take away d minus k. And it has to act freely on the k minus 1 sphere. In our hypotheses, we've assumed that k is odd. So k minus 1 is an even dimensional sphere. So using some topology, you can show that the only such gamma we can work with, since it's fixed point free, must have order 2, which is lovely because that sticks us right into the situation where the Krautschuk polynomials are giving us that first heat invariant, the 0th heat invariant associated to the stratum n. So if we sum that 0th heat invariant corresponding to the P spectrum over all possible singular strata n of codimension k, you can show that that is a spectral invariant, so we can detect that sum. And then when you look at our expression for those 0th heat invariants, you do see the volume of each of those strata appearing right there. Since we've assumed that the Krautschuk polynomial does not vanish, we can use this to compute the volume of the singular set, because it's going to be the volume of all these highest dimensional strata all added up right there. Let's see. So some results there from the P spectrum. I think I'll wrap up by just checking in on my current work in progress. I have been working with an undergraduate here at my college on this project, and I'll keep working. There's still work to do. So what are we asking in this current work? So here's this corollary to the codimension less than or equal to 3 result. The corollary said for d less than or equal to 3, the 0 spectrum and the 1 spectrum can detect the singular set of an orbifold. Our question is, what about dimension 4? Wouldn't it be nice if we could bump this theorem up to dimension 4? And not just nice, but there's a sort of fact about this case that just is vexing. So that's why I want to work on it. So in dimension 4, if you jump down a dimension to codimension 1 to dimension 3, 3 is an opposite parity. So if you have a stratum of dimension 3, that would be an opposite parity stratum. So we can detect it using just the Laplace spectrum. If you jump down to 2, then that's codimension 2. So this theorem at the top takes care of that. And then if you jump down to a one-dimensional singular stratum, so if that's your, if you have such a stratum, that's also opposite parity to 4. So the only thing getting in the way of extending this corollary to dimension 4 are the 0 strata present in a 4-dimensional orbifold. In some sense, these little strata are at the moment too small to extend our result. So with the student, we've been examining if we can, in the case of a 4-dimensional orbifold with only 0 strata, can we use heat invariance to detect the presence of those isolated singular points? And it's interesting because an isolated singular point corresponds to an action in 4 dimensions that just fixes that central point. You can't fix an axis. What am I trying to say? Let's see. So an isolated singular point, you can't have like a reflection through that point, or otherwise you'll have a higher dimensional stratum. So if you are looking at orthogonal actions in dimension 4, fixing just the origin, you can restrict those actions to the 3 sphere, and all of a sudden you're looking at free actions of finite orthogonal groups on the 3 sphere, which are lovely and well understood. There's a lot of literature to work with them. So that gives us some hope that we can do some computations. The hard part is that when you're working with such a low dimensional stratum, the 0 stratum, the heat invariants that we need to work with to get a contradiction similar to the one for this theorem end up being the A2 heat invariant. in the manifold setting, and that involves integrals of norms of the curvature. So the Riemannian curvature tensor, the Ricci curvature, and the scalar curvature, which is hard. So my student and I, this is Nicholas Dill, is his name, have assumed constant Ricci curvature and gotten a teeny case when we're only acting by rotations on our three-sphere super simple lens spaces. And we seem to have gotten progress there in the constant Ricci curvature setting, which has been very, very interesting. I think I will stop there, though, and I welcome questions. Thank you.
Thank you, Liz, for a very nice talk. Are there any questions?
Liz?
Yeah.
Very, very nice talk, Liz. I wonder whether the same problem as you have, what happens if you impose that both the orbifold and the manifold are locally homogeneous? Okay, probably not covered by the same universal cover, but you assume that both are homogeneous. Do these help you in some way? Does the heat invariance make simpler?
It's a great question. I don't know. So you're asking if you have a locally homogeneous manifold and an orbifold, will that be an obstruction to isospectrality? I don't know.
Okay.
Yeah, great question, though.
Yeah, there's work in what, 3 dimensions by let's see, Craig Sutton, and was it Ben Schmidt and Sam Lin, I guess, but that's in dimension 3.
Yeah,
Yeah.
that's in dimension 3, yes.
Yeah. So, and you're looking at dimension 4, so yeah. Are there other questions? Or well, if not, thank you again.
Yeah, pleasure.
The-